Fabini's theorem states that you can switch the order of integration for constants, for constant limits, if you have a rectangular region. And we'll see by the end of today that it doesn't work that easily if your region is not a rectangular region. And then the second thing that we talked about was a special case where if you have a function that you can separate factors, then you can take them out separately and integrate them separately. So this is different from an iterated integral, because an iterated integral is something that you integrate from inside out. This special case is something that you can set aside and integrate separately. And so as a quick example, maybe, because I don't want to spend too much time on this, as a quick example, maybe we can think about this where a function f of x, y is equal to maybe x times e to the y, where your domain, I'll simplify this. I won't write x and y. Your domain is just going to go from, let's say, 0 to 1 by 0 to 2 or something like that. Or let's call it R, sorry, since it's a rectangular region. And so the integral of this is going to be an iterated integral of the function x e to the y, and then we can integrate with respect to x first. We'll say dx, and then our x value or x limits are going to go from 0 to 1, and then we'll integrate with respect to y, dy, from 0 to 2. Now, I'm going to go two different ways here. And one way would be an iterated integral that we'll do. And maybe the iterated integral can go down this way, where we would integrate the inside first and then integrate the outside. So the inside integral is an integral of x e to the y dx. So integrate with respect to x here. E to the y is constant, and so it'll be 1/2 x squared e to the y, and we're going to evaluate this where our x values go from 0 to 1. And then we put 1 and 0 in. So if we put 1 in, we get 1/2 e to the y minus, and then we get 0 times e to the y. And then we integrate this with respect to y. Integral of e to the y is just e to the y, and now you got the 1/2. And then this is going to be 1/2, and then you put 2 in there, e squared, and you put 0 in there, you get e to the 0, which is equal to 1. And so this is your result. Okay, now we can do Fabini's theorem and check by switching the order of integration here. Instead of integrating with respect to x first, you can integrate with respect to y. And what I'll do is I'll write that down here, but I'm not going to follow through. But you could have done this integral from 0 to 1 and 0 to 2 instead of going from 0 to 2, 0 to 1. So the inner integral would be x e to the y dy. Your y goes from 0 to 2. And then your x goes from 0 to 1. And so you notice that if you switch the order of integration by Fabini's theorem, then we should get the same result. And again, I'm not going to do it. We'll just assume that we're going to get the same result. Okay, but I'm more concerned with this special case where this function can actually be written as two different functions being multiplied together. They're factors. Okay. And if we take a look at that carefully, we can play around with this idea of, you know how when we integrate 2x, we can pretend 2 is a constant, you can bring it outside of the integral. So if we take a look at the inner integral here, inside of this integral, we're integrating with respect to x, right? So e to the y is a constant with respect to x. So we could take that out. And then we would still have the integral from 0 to 1 of x dx. Okay? So now, I'm looking at this integral over here. We can lift the brackets. And then the integral that we're looking at has e to the y times another something in there. Now the something, I just underlined, is a constant with respect to y. So imagine taking this constant with respect to y and moving outside of the bigger integral. This has no y's in it, so I can leave that outside as a constant. And then I took it outside of this integral, 0 to 2, e to the y dy. So because we were able to factor into two factors where one factor is constant with respect to x, the other factor is constant with respect to y, we can actually split this up to two different integrals. And then if you've gone this far, you could just take the integral of each one separately. I think that was the idea here, is that it'd be easier to follow. And if you take the integral of x, it's x squared over 2 from 0 to 1, and then that result is going to be 1/2 minus 0. And then if you take the integral of e to the x or e to the y, that's e to the y from 0 to 2, and then you put 2 in there, and then you put 1 in there, and or you put 0 in there, and you're going to get the same result as you did when we did the iterated integral. Now you have to be careful. You can only do this when you can factor out, when you can factor it in, you factor the function into two different functions that are just x or just y. So, in other words, if you have something that you can't factor into two different functions of just x and just y, then you can't split it up the way we did in this special case. So you'll have to use the iterated integral for this one. So you can't write something like x squared plus y squared into two factors with just x on one factor and just y's in the other factor, so you can't use that special case for this one. But we will run into the special case quite a bit, actually, later on, so we're just going to jump on it and take advantage of it. Okay, so it turns out that if you have a rectangular region, there's a lot of neat little properties that you can work with. But when your region is no longer rectangular, say you have a triangular region or some part of a parabola or some part of some exponential function, then it's not going to be so easy. Not that it's hard, but it's not going to be as easy as what we've been dealing with. All right, so let's say, I think this is 15.3 now. My dot doesn't work. There it goes. My L doesn't work. My O doesn't work. It's the ring finger on the right hand on the keyboard that doesn't work. Oh, whoa! Sorry. Need a new computer. I think I'm going to steal some problems from the let's see which one looks easy. That looks easy. So it's quite rare that we're going to look at rectangular regions, and most of the applications and the integrals that you guys are going to be doing are going to be on more general regions. So what I want you to do is, although this is something visually that's happening in 3 dimensions, it'd be great if you can draw it in 3 dimensions, but I'm not going to expect that. But I do want you to be able to draw this in 2D. And what you're going to draw in general is going to be the region that you're integrating over. So you want to get back to being able to do that. I think in Calc 2, when you took some regions and rotated around some axis or something, volumes of revolution business, you got used to looking at a set of inequalities like this and finding out a region. Okay, so it's the same idea, except you don't have to rotate it, you just have to identify the region. All right, so what we want to do is we want to be able to draw this region and then find out some information about this region. So we're going to go from 0 to pi in x and 0 to sine x in the y. So the sine function, I think, starts from the origin and goes on. And so we're bounded by 0 on the bottom and by sine x on top. And then we're bounded by x equals 0 and x equals pi. And so you should be able to see that our region is actually this thing. Now what we're doing here is you're imagining that this thing is on the xy plane, right? And then you have some surface up on top. In this case, z is equal to 4x. It looks like it's just going to be a plane, but in any case, it's some surface-looking thing up on top. And then you're trying to find the volume below this surface, and that's above this region. And so what you're going to do for this first example is that, you know those slices of bread that we were talking about? We're going to get a slice of bread going vertically, looking at it from the top. And so when you slice it that way, you're going to hold x fixed. And then your y is going to range from y is equal to 0 to y is equal to sine x. So notice that it's not a rectangular region anymore, and your y is now going to go from a number 0 to a function x. So that's for a fixed x. And if we change the x, say go to another fixed x, you're going to go from 0 to a different y value, but it's still going to be sine of whatever that x is equal to. Okay? So you're going to make your bread slices, and your bread slices are always going to be from 0 to x. So for me, I like to write this down. I like to keep track of my limits for the y value, and my limits for the y value go from 0 to sine of x. So being that those are the slices, that's going to go in the inner integral. Okay, so my inner integral is going to integrate this 4x, and then I'm going to integrate with respect to y. So these, for each slice, I'm going to run along the y from 0 to some function. So dy from 0 to sine of x. Okay, now how am I going to stack up my bread? Well, I'm going to stack up my bread with x values starting from 0 to x is equal to pi. So my x is going to go from 0 to pi, and this will be my outer integral. So my outer integral is going to go from 0 to pi dx. Yes? Because if we think about the bread slices, each slice is going to have a different shape. And the shape is going to go from 0 to, if I follow just the y measurement of this, parallel to the y-axis. It looks like I'm going to go y is equal to 0 to y is equal to this function over here. And so if I fix my y at some place, it's going to go from 0 to sine x. And if I fix it to another place, it's still going to go from 0 to sine x. So it looks like as I make my slices all the way from 0 to pi, my y values are always going to go from 0 to the top function, which is sine x. That's in the y direction, correct. And so my y limits will be 0 to sine x. Yeah, so the inner integral would be the slices. So you imagine how wide your bread's going to be. And then the outer integral, you can imagine that to be how you stack up your bread slices. And you're going to stack them up from 0 to pi. Yeah?
So is the inner interval always going to be the norm of the variable bound?
How about you say it the other way?
Is the outer interval always going to be constant?
Yes. Did you hear what he said? If there's anything to take out from today, it's just that your outer integral limits must be constant. Exclamation point, exclamation point, exclamation point. Well, think about this. We want a value out of this. So when we do an integral, a definite integral is what this is. Whenever we do a definite integral, we have a result that's going to be a value, a constant, a number. Now, if your outer integral happens to have a function in it of with a variable that's indeterminate, or that's not, it's a variable, then when you put in those values with the variable in it, your result is going to have a variable in it. So,
is there a situation where you want to do that?
Not in this class. That would happen if it's in the middle of some sort of computation, if you're doing a triple or quadruple integral or something like that. That might happen. But in general, we want the outer limits to be constants. Okay? So I do want to make a big deal out of it. Outer limits must be constants. Because I don't want to see that kind of mistake on the test. So what can we do to make sure that nobody makes that mistake on the test?
Will you write the roll on the top of the test?
No, I'm not going to write.
Well,
It should be embedded in your heads.
think of it this way. If you don't have constants, if there are non-constants in the final one, then that implies
You're not
that
getting an answer to the question.
that implies that your answer is indent.
It has a variable in it, right?
Contextualize your answer, figure it out.
Maybe you can have this explain or justify.
Well,
Or you can have a
you can write it 100 times if you want. I don't know. Whatever. Don't make that mistake. Please, please, please don't make that mistake on the test. Okay. Should we do this? I suppose we should. So let's actually compute the integral. So this is something that's an iterated integral. And you know how that special case we were just able to take things out? Now, it looks like we're integrating this with respect to y, and this is a constant. Okay, but unfortunately we can't split it up because the limits are not constant. So like I said, that previous section that we were just working on where we had constant limits, where we had rectangular regions, that was those are really nice parameters for us, but that's not going to happen all the time. And then if it doesn't happen, you can't split this up to two integrals. You can still take this 4x out of this integral with respect to y, but you can't split it up to two different integrals because you have a sine x as an upper limit. So let's just take this integral. We're going to go from 0 to pi. The integral of 4x with respect to y is what? 4xy, and then you're going to evaluate from 0 to sine x. Now this is where it gets really important to know what you just integrated with respect to. And so that's why I like to include that I integrated with respect to y, so the limits that I'm going to evaluate are going to be y limits. So when I put 0 in, I know that I'm going to put 0 in for y and not the other variable that's still hanging around. So I'll put sine x in for y and 0 in for y. Then we have the integral from 0 to pi of 4x sine x. Oh.
Isn't that one of those unsolvable integrals?
It's not unsolvable.
Oh, wait.
It's what?
Like sin x minus x cosine x?
Okay, thanks. Well, I'm just going to take your word for it.
I'm thinking sin x over x.
Wait, what is it?
Sin x minus x.
Integration by parts. Okay, I'm not going to go through that. But you should. So you put pi in there, sine of pi, is that 0? Yeah, that's 0. Cosine of pi is not 0. So how am I going to do this? 4, 0, pi. Cosine of pi is -1. And then sine of 0 is 0. This is going to be 0 also. Oof. Okay, so I think all we have left is positive 4 pi. Okay, is that good? Oh, I should check. I think this is a problem that we just took from here, huh? So in the book, they call it type 1 and type 2 region. I never remember which one's type 1 and which one's type 2. So I don't think that the name of the type is important. I think what's more important is just to be able to come up with the limits and then be able to identify which one's the inner integral, which one's the outer integral. All right, let's do another one. Let's try number 10. It looks kind of interesting. And then in a little bit I'll start kind of weaseling into some shortcuts so that we don't always have to talk about sliced bread. So set up the iterated integral for both orders of integration, then evaluate the double integral using the easier order. All right, so we have the integrand is easy, it's just y. That's nice. So it's a double integral of y dA, and then we have our region is going to be bounded by, it looks like a line, and x minus x equals y squared. I think that's a sideways parabola. But let's see how this looks like. X is what do you call it? This is a line, slope 1, y-intercept negative 20. So I'm assuming the x is also going to intersect the 20 since the slope is equal to 1. We have a sideways parabola, x is equal to y squared, so so this looks like it's our region. We agree to this? I mean, where's our region? Can you tell where your region is? It's like a, yeah, the thing. So, yeah, I mean, I've seen people in Calc 2 get tripped up with what the region is after they graph all the different parts of, all the different graphs that they show you, and they say it's somewhere in here, and then there's this triangle over here, there's this triangle over there, or maybe not triangular, there's some other spaces all over the place, and you just have to know which one is the actual region before you get started. All right, it says set up the iterated integral using both orders of integration. So let's, again, for this problem, let's imagine sliced bread. And let's imagine slicing this bread along the, last time we cut it along the x. Let's try cutting it along the x again and see what happens. So if we cut it along the x, your slices would look something like this, right? So if I look at the length of the slices, I'm looking at essentially some y values. So where does my y range from? What are my y values? What is y being bounded by? Looks like the line is the lower bound, so if I solve for y, well, y is already solved for here, x minus 20. Oh, where?
It's touching at the where the two functions intersect. To the left of that, the lower bound is y equals x equals y squared.
So right here, where I'm pointing at? So it looks like we have a bit of an issue here, right? In terms of y? Well, let's finish this thought first. And I want to finish this thought, one, because they say set up both integrations, and two, because it's harder. And there are going to be some times where you're doing these things. There's one way is going to be easier than the other, as they had mentioned. And so I want you to know when it's a little too difficult and when you should try it the other way. Harrison? Yeah, so that's going to have to be our plan if we want to integrate with respect to y first, if we make our slices as we identified here. So in doing so, we're going to have to set this up as two different regions. One of them is this region, and then the other one is the other region. So let's redo this. And let's identify this as two different regions. So for this region over here, if we're going to make our slices vertical like this, we would need to identify y equals limits, y equals 2. So what's the bottom function? Y equals what? Yeah, so this function over here is x is equal to y squared, and what you want to do is represent it as a y equals function. So you can say, if you solve for y here, y equals to, oh, you're going to take the square root, so there's a plus and minus. And that's exactly the plus and minus that's happening here. So that y equals negative square root of x is the bottom limit, and then y equals a positive square root of x is the top limit. So here, your y goes from negative square root of x to positive square root of x. So these are the inequalities that I want you to get used to setting up. Now when you set up these inequalities, you're integrating with respect to y first and then with respect to x, so eventually you'll need to integrate with respect to x. What are my x limits going to be? 0 to what? Oh yeah, we have to figure out what this intersection is. So let's do that down below. Or how are we going to figure out what the intersection is? Set them equal to each other, and we should get two solutions, right? So we'll set them equal to each other. Find intersection. And they're both y equals to, no they're not. Oh, but I can put the x in there, whatever. Y is equal to x minus 20, and x equals y squared. So let's put y squared in there. Looks like I can do y squared minus y minus 20 equals 0 and factor it. Y minus 5, y plus 4. And so I'm going to get y values here. Y is equal to positive 5 and negative 4. Now, does that make sense? Positive 5, negative 4? Those are my y values, right? So this must be the negative 4 one. And this must be the positive 5 one. So now I need to figure out what the x value is, because I think that's what we're going, right? So x equals, when you can use either of these, they should work. Let's use y equals x minus 20, and let's put 5 in there. And we get y equals, x equals, yeah, something like that. Sorry. Oh, here, let's use this one. X equals y squared, since we have a y. So x equals 5. I mean, y. We need both of them. So when y is equal to 5, x is 25. What? Is that right? And when y is equal to negative 4, x equals 16. Does that make sense in our graph? So this is 20 over here, right? So this intersection here should be a number less than 20, and then the intersection here should be a number bigger than 20. So it looks like it makes sense. All right, so now what was the limits again? For x, x goes from 0 to 16. So that gives us one integral, and now we have to come up with the other integral. So the limits for the other integral will be, for your y limits, remember your y is the one that's going to be touching the functions. This is the inner integral. Your y is going to go from what to what? So for each slice over here, my lower y limit is going to be what? So the lower is going to be the line. So y is equal to x minus 20, so y is equal to x minus 20 is the lower limit. And then the upper limit is y equals what? Square root of x, the positive one, right? What are my x limits? More importantly, they are constants. All right, so to figure this out, your integral, you're actually going to have to add two integrals. So you're going to be the integral from minus square root of x to positive square root of x, and the integrand is just y. Dy, and then your outer integral is going to be the integral from 0 to 16 with respect to x. So that'll give you the volume above this first part, and then the second part would be an integral, again the integrand is y, but your y limit, dy, your y limits are going to go from x minus 20 to square root of x. And then your x limits are constants, going to go from 16 to 25. So this is one way to do the problem. Okay? So let's try it a different way. I need to redraw this. Okay, so instead of making your slices parallel to the y-axis, what if you make your slices parallel to the x-axis instead? What if you make your slices like that? Now, if you do all the slices, and you notice, one thing that you notice is that at every single slice, you're always going to be slicing from one function to another function, and nowhere in this region do you need to change functions. So that is going to be an advantage for us. So in our slices, the idea here is we're going to fix y initially, and then we're going to need to find x values or x limits for our inner integral. So our inner integral, we're always going to go from lesser to greater. Our inner integral is going to go from this function, and I need to write this, since this is an x limit, I need to write this as an x equals 2 function. What's x equal to in this case? This function right here, y squared. So that's my lower limit. And then my upper limit up here is going to be x equals to what? What is it? Y plus 20? Now, as I make those slices with the fixed y, once I figure out those slices, I'm going to see how, where am I going to start, and when am I going to end stacking up my slices. So where do I start? Y equals -4. Y equals to 5. Constant limits. So now we have our inner integral. Remember, the integrand is just y. Our inner integral is going to be with respect to x. So this dx. And your limits are going to be, the lower limit is y squared, the upper limit is y plus 10. That's the inside integral. The outer integral is going to be integrated with respect to y, and my y limits are going to go from -4 to 5. What? 20. Where did 10 come from? Oh, that looks like a 10. All right. So here I calculate one integral to give me the answer. The previous one I'd have to calculate 2 integrals. So clearly this one looks a lot easier to deal with. Okay? Can we not do it and say that we did? Oh well, I was going to use Mathematica, but is that okay? Does it look fun? It's fun. It's so much fun. All right, what is it?
You want the fraction? 7,533 divided by 5.
I hope so too. Ah, bummer. Now I really have to find it. All right, fine. That's my palette. Definite integral. DINTT. That's what I thought I did. Oh. Is this a plus? 243 over 4. Okay. All right, let's do another one. Should you do this one? So the integrand is 9x times cosine y, and then we have to figure out what our region is. Our region starts off with y is equal to 0. I think that's the x-axis, yeah? Y is equal to x squared. And x is equal to 9. X equals 9. Vertical axis? I mean vertical line. Can you find your region? Yep. So in this case, I think we have a choice in integrating with respect to x and to y based on the region. Now, based on the integrand, what's inside of the integral, we might want to go one way or the other. But in this case, we have a little bit of a choice as to integrate with respect to x first or with respect to y first. So why don't we just randomly choose? You guys want to pick x or y? Y. So here's what I want you to do now for doing these types of problems. You need to look at the region and decide for yourself what would be more appropriate integrating with respect to x or y. Once you've established that in your head, then write down the inequalities, and whatever you're going to integrate with respect to first, you'll put that up on top and convince yourself that that's going to be the inner integral. And then the outer integral over here, you know that you're going to have to put constants. Okay? If for some reason the graph is not allowing you to put constants, then you did something wrong. Or maybe you need to switch the order, or maybe you don't know what you're doing, or something. So what you want to do is, once you figure out what you're going to integrate with respect to first, draw a line parallel to this axis. Okay, we decided we're going to integrate with respect to the y-axis first, right? You're going to draw a line parallel to the y-axis, and then you're going to note when you're going to enter the region and when you're going to exit the region. Okay, so the line parallel to the y-axis is going to enter the region somewhere. And then you need to identify that region with respect to x. Y is equal to something. So what region did what graph did I pass through to enter the region? Yeah? Y equals 0. So that's going to be my lower limit. Now at some point you're inside of the region, and at some time or some point you're going to exit the region. The question is now, what function did you get out of the region from? X squared in this case. So once you figure that out, you have your limits. Draw a line parallel to the axis, in this case the y-axis. Figure out when you entered and when you exited. And those will be your limits. Okay? Outer limits have to be constant. So when did you start? And when did you get out? When did you start? X equal, and remember that these are x values that you're putting. So you started with x is equal to 0, and when did you finish? Well, x is equal to 9 in this case. Okay? All right, so here's your integral. Inside integral, well, let's write the integrand first, 9x cosine y. And the inner integral is with respect to y. Well, remember that when we write down our limits, because the limits are not constant, it's not going to happen so easily. Okay, so you write down the integral sign, you write down your integrand, you write down d, and then whatever variable you're going to integrate with respect to first, so that's a y, and then you put the limits down for the y. And then you write your second integral on the outside, and then d, whatever you're going to integrate with respect to last, and then the limits for that. And here you go. Okay? Dot, dot, dot. Any questions? Now, let's do one of my favorite problems. We have time. We can do this in 2 minutes. Let's take a look at this problem where the integrand is 13x e to the x squared dx. You integrate with respect to x from 3y to 9. And the idea behind something like this is that we don't have a formula for integrating e to the x squared with respect to x. Okay? There's no u substitution, there's no integration by parts to do this, and it's not going to work. So, but it comes up so often that people made something up. And if you put this into Wolfram Alpha or Mathematica, it'll give you the ERF function. ERF. They call it an error function. Earth. Anyways, we're not going to talk about Earth. So instead of trying to do it with respect to x first, what if we switch this and integrate with respect to y? Well, how are you going to switch that? Well, can we do this? Because we had a theorem that says Fubini's theorem says that we can just switch the order. And just imagine if you can switch this, we're going to integrate with respect to y first. And then this is a constant, so you'll have a y come out, right? And then by doing some other substitution, you can eventually integrate with respect to x. So this is doable, right? What's wrong with this? That should have been in red. Oh, that should have been in dark red. Constant limits on the outside. Can't just switch this. All right? So that's strike two. Speaking of strike two, you guys watch a game. So what we need to do is we need to take our limits, take a look at our limits. And our limits, you have to write this. So we're essentially working backwards. Our x limits go from 3y to 9, and our y limits go from 0 to 3. So what we want to do is we essentially want to work backwards, peel the limits out of the integral itself, try to imagine how this is going to look like in the graph. X is equal to 3y, so that's a slope of 1/3, I think. Wait, slope of 1/3 is flatter. X is equal to 9. Y goes from 0 to 3. So somehow you need to extract a region out of the limits of integration. And then from this region, try to come up with a new integral where you're going to integrate with respect to y first and then x. So how do we do that? If you integrate with respect to y first, draw a line parallel to the y-axis. You enter the region where? Y equals 0. You exit the region where? Y equals 1/3 x. And then your x limits go from 0 to 9. So if you rewrite this integral, 13e to the x squared, and this time integrate with respect to y first, from 0 to 1/3 x, and then integrate with respect to x from 0 to 9, you're actually going to be able to do this integral by hand. Because when you integrate the inside with respect to y, e to the x squared is constant, so you'll have a y come out of there. And then when you're done with the inside integral, when you finally integrate with respect to x, you're going to see that you're going to be able to use a simple u substitution. Should we do it? No. All right, let's do it. 13e to the x squared times y. Y goes from 0 to 1/3 x. And you put 1/3 x and you put 0 in for y and you get 0, right? And so now you're going to integrate from 0 to 9, 13 over 3 x e to the x squared dx. So 13 over 3 is a constant. This little bit over here, you're going to do a simple u substitution. Cancel the x. And then now can I put dot, dot, dot here and say it's doable, unlike the first two tries that we had. Okay. All right. Ran a bit over, sorry. But this is just too exciting to let go. The suspense was killing me. We just had to finish it, even though it's not done. The quiz will be on the second derivative test. Tomorrow, quiz, second derivative test. Good luck. Goodbye.